My name is Jonathan Chu. I work for the Solaris Kernel group. I'm the tech lead for our CMT and NUMA optimizations in Solaris. Today I'm going to talk about basically what optimizations we've done for NUMA and CMT on Opteron. And so for Solaris, basically we have some abstractions, and most of the work that I've done for Opteron has been for NUMA. The abstraction we added to Solaris to help the operating system understand which CPUs and memory are close to each other in a NUMA machine, so that the operating system can optimize for that locality and give the best performance possible, is something called locality groups, or L groups. And the great thing that we got from working with AMD and working on Opteron for this is that it gave us the opportunity to work on a system where we had more than 2 levels of latency or locality, because all our systems that we worked on prior to that only had 2 levels of locality or latency, and were basically a little bit simpler. So AMD Opterons gave us the opportunity to do something a little more challenging and interesting. So let me explain what the idea behind L groups, because I think the abstraction itself is key. And once you understand the abstraction, then everything else sort of falls out. So if we had an Opteron machine that had four processor chips, right? And they're connected together into this sort of topology, right? So they're basically in a ring. And for Opteron, basically each processor socket has some number of CPUs in it and has some local memory that the CPUs are connected to. And then the other nodes are similar. They basically have some local processors, some local memory, et cetera, just the same. So what NUMA is basically this idea that some processors are closer to some memory than others, and basically all the processors can access all the memory. They can access their own local memory, and they can access the memory that's remote to them, even if it's a few hops away. They can still access this memory. But it takes longer for them to access the memory that isn't local to them. And so this memory that's local to, say, these processors, they can access the fastest, and then this memory next fastest, and this one, which is 2 hops away, the least, and would take them the most amount of time to actually access. So what we did in Solaris is we wanted to come up with some way to model this, right? So that we could do optimizations based on locality for it. So what we did was we modeled the latency topology of the system. And let me explain what I mean by that. Is that, so if we number these nodes like 0, 2, 1, and 3, for example, and then we basically make a latency topology that helps us show us how these nodes relate to each other. So, basically you have one that corresponds to 0, and this L group, or this is basically our L group abstraction, which is our locality group abstraction. So you have the group of CPUs and memory and potentially I/O resources that are all close together, captured in this grouping, or this L group. And in this picture, I'm going to make 0 correspond to node 0, and then we'll have one for node 1, and node 2, and node 3. So each of these correspond to each of the node, or the CPUs and memory and potentially I/O devices that are local to each other in each of these nodes. And so 0 goes with 0, 1 with 1, 2 with 2, etc., and three with three. So for our L group topology, what we do is we model the latency topology by making it so that, making a little tree that shows the relationship. So the parent of 0 would be everything that's within one hop of node 0. So basically, it's all the resources that are next closest after local, right? So then, in this case, that would be 0, 1, and 2 are all within one hop of 0. So they're next closest. And then its parent is what's next closest after that, which is everything that's within 2 hops, right? So that'd be 0, 1, 2, and 3, because 3 is 2 hops away from 0, which is basically this L group we call the root L group because basically it contains everything in the system. And then comparably, you would have an intermediate L group for 1, 2, and 3 that all connect to this root L group, and we basically end up making this tree that models the latency topology of the machine. And so then once we have this, the operating system understands this, or has this, understands it, and can actually do optimizations based on it. So the idea is that basically if you have a software thread or an application, the operating system by default will assign the thread when it gets created to one of these L groups. And basically this thread will have an affinity for that L group. And by affinity, I mean that the operating system will know that basically this thread likes this L group. And so from now on, what I should do is I should try to run it on the CPUs in this L group. I should try to allocate its memory there. In that way, when I do that, it should always get local resources. It should run on a CPU here and allocate memory here, and then it'll get the best performance because this memory and this CPU are closest together. You'll get the lowest latency, and consequently the best performance. And so then, what we do then is we use this latency topology to do this optimization where if you can't get the resources in your home L group, then you'll walk this latency topology and try to get the next nearest resources. So if you can't get local resources within L group, your home L group, which in this case is L group 0 and corresponds to node 0, you try to go to your parent and try to get any of the resources that are available within one hop. So that, in this case, would mean anything from 0, 1, and 2. And then if you can't get it from there, then you try from its parent, and you keep going all the way up until you get to the root. And then once you get to the root, you should be able to get it because that captures all the resources in the machine. And so in this way, you'll always try to get what's closest as possible to the thread that you're trying to optimize for. And that way you get the best performance. No matter, if resources aren't available, you just try to get the next nearest thing. So in that way, we optimize for NUMA. And you can see that using this topology, there's basically two ways we can optimize, which capture the basic ways that we do this. Is that you're either optimizing for affinity, which is where you try to get something close to your home, or you're optimizing for load balancing, where you start from the top and you work your way down, and basically then you can spread things out better. And then we do both these optimizations, one for affinity, one for load balancing, so that we'll optimize for the lowest latency, but at the same time we're going to try not to create any sort of hotspots, and so we load balance across the system at the same time. So in that way, then, say in this case, L group 0 doesn't get overloaded. So that's the basic idea with L groups. And it was our work on Opteron that motivated us to come up with this abstraction and be able to do these sorts of optimizations. If you want more information about what we do in Solaris to optimize for NUMA, there's a set of slides that I put out on Open Solaris, and it's inside the performance community. There's a update or an overview on MPO, and MPO stands for Memory Placement Optimization, which is the marketing name for this feature. Then for developers, there's also a programmer's interface guide that you can find at docs.sun.com. It's part of the Solaris collection of documentation. So that's it.